Welcome back, Dynamics fans. Let's carry on here. We're doing problems about forces, and this one has friction in it in detail, which we haven't seen yet in the problems, but it's nothing too bad. We have the ground, and on it we have a sled. We'll go classic toboggan. And they say the weight is 52 newtons. That means the gravitational force is 52 newtons. Someone did m times g and came up with 52 for the answer. So fine, we'll take that. Now, it's worth noting, because they did m times g to get this, we could work backwards and get the mass of the sled if we need to. I'm not sure if we will, but it's good to know that that's available. And because sleds don't normally sink into the ground, especially when it's cement, there's a normal force here canceling out the weight, and that's also 52 newtons. So we have F normal there, we have F grav there for pulling down, and then they say somebody's pulling on the sled. We'll call that an applied force. That's the term we usually use, and that's 18 newtons. And there's this magic phrase here, constant speed. Constant speed means your velocity is not changing, and that means your acceleration is zero. And because of F net equals ma, that means the net force is whatever your mass is times zero, so the net force is zero. If you're at constant speed, it means there's no net force on you. All of your forces are canceling out, and that's why you're just buzzing along at constant speed. You're like the thing in Newton's first law where they said an object will remain in motion if it isn't acted on by external unbalanced forces. If you're just going at constant speed, that means there are no unbalanced forces on you. They're all canceling out. So, we know these 52s are canceling out. The other thing that means is that if you're at constant velocity, the friction must be 18 this way. F friction equals 18 newtons. That way the applied force and the friction force are canceling, and that's why you're staying at constant velocity. So the friction is 18, and what they're asking for is the coefficient of friction, which is a number that comes up in our friction formula. The way you find friction, you take, this is the Greek letter mu, it looks like a letter U but with a long front on it, times the normal force. So the amount of friction force you generate is the coefficient of friction, which is a measure of how sticky the contact is between two surfaces. If you're doing like Velcro on Velcro, this is extremely high. If you're doing boots on concrete, it's reasonably high. If you're doing boots on ice, it's low. If you're doing boots on wet ice, it's extremely low. And if you do wet ice on Teflon, it's almost zero. There's hardly any stick in a situation like that. So this number just tells you the stickiness. And F normal is the normal force. It's how hard are these two surfaces grinding against each other. In this case, the answer is 52 newtons. So if we plug in what we know here, the friction force is 18 newtons, found it over here, equals mu, don't know it, times our normal force is 52 newtons. So if we want to solve for mu, we divide both sides by 52. And 18 divided by 52 is going to be like 0.34 or something like that. Let me pull out my calculator app. 18 divided by 52. Yeah, 0.35 is our coefficient of friction. A coefficient of friction doesn't have any units, it's just a number. It can be more than 1. It can't be less than 0. 0 means frictionless. But that's the overall rating of how sticky the sled on cement contact is. Those surfaces have some drag, but not a huge amount. Can we get through one more of these? I think I've been doing 2 per video so far, so let's try to stick with that. Okay, determine the amount of force needed to lift a 366 gram textbook at, here it is again, constant speed. Constant speed means no acceleration, means zero net force, and that means all the forces on it are canceling out. So if this is our book, and it's 0.366 kilograms, get your grams out of here, those are for chemistry. If that's our mass, then the gravitational force on this thing, assuming it's on Earth where most of the textbooks are, is m times g. It's going to be 0.366 times 9.81. Calculator is punched and we get 3.59 newtons. So if the weight of this book is 3.59 newtons, then if you lift it with 3.59 newtons, that'll be enough to cancel out its weight, and you'll keep it at a constant speed. However fast it was going, you'll just keep it going at that speed. Or if you're holding it still, then it will remain still, because your lift is canceling out its weight. So Earth pulls down on your book with 3.59 newtons. If you want its velocity to remain steady at 0 or any other number, you have to hold it up with 3.59 newtons of strength. That way you cancel out the weight and everything stays the way it is. Okay. Now, same book. They're changing things up here. We still have our book. I don't know why I keep drawing the cover and the pages. It just feels good. The weight of the book is 3.59 newtons. Earth pulls down with that amount. And now this slightly wimpy student is generating not enough force on the book. We said 3.59 would hold it up. They're only producing 2.5 newtons upward. In other words, they're kind of letting it fall. I mean, this is what happens if you lay a book down on a table. You're holding it in your hand, and then you allow it to drop under control until it gets to where you want it, and then you let go of it. So they're not holding up all of the book's weight. That means it should move downward a certain amount. And we can see how much, because we have F net equals MA. The net force consists of a positive 2.5 from the student's lift, and a negative 3.59 from gravity pulling down. And that equals the mass of the book, which they said is 0.366 kilograms, times an A we don't know. 2.5 minus 3.59 is minus 1.09, and that equals 0.366 times A. So if we want to solve for A, we divide both sides by 0.366. A is multiplied by this. We want to do the opposite. We divide by that amount. You probably remember that because you're in Physics 30, but just in case you haven't thought about it for a while, that's what we're doing. So 1.09 negative divided by 0.366, and we get that our acceleration is negative 2.98 meters per second squared. If you just drop a book, it falls at minus 9.81. This is not a drop. They're still lifting it a little bit, so it falls, quote unquote, but not as fast as normal. And because our data here all had 3 significant digits, 2.98 is the correct amount of precision for our answer.